So welcome back to Particle Physics and the Standard Model. This is lecture 19, and last time we saw why we needed quantum field theory, the language of quantum operators that are functions of position and time that act on Fock space all over the universe. We saw that it explains away very nice features like indistinguishable particles, spin statistics theorem, antiparticles, and so on and so forth, right? And then we wrapped up with an introduction to natural units, and I promised you that it will make life easier. So you should practice thinking in terms of natural units, and we will now start seeing an immediate application as we start building up some basic things about quantum field theory. Okay? Okay. So I am going to start with a principle of physics that seems to be very fundamental and yet beyond the grasp of many people, including experts. Nobody really understands why this principle seems to work again and again in nature. It's still an area of active research. Nevertheless, it works for us, and so we use it. Okay, and that is the action principle. Remember the action principle from classical mechanics, right? All of Newton's dynamics were reformulated in terms of Lagrangians and Hamiltonians, correct? And you use a Lagrangian to write down an action, and the action principle says what? That the trajectory of an object is determined by minimization of this action. Agreed? So let's write out to jog your memory. This is the action, correct? Where in classical mechanics what is the L? That was the Lagrangian. What are T and U? T is the kinetic energy and U is the potential energy, correct? And what happens when you minimize the action? You get an equation of motion correct, and in the Newtonian dynamics case it turned out to be what? F equal to ma, right? Go ahead and work this out again. Take a simple case, put in a potential energy and convince yourself that this is true, right? And what is an equation of motion also called? The Euler-Lagrange equation, correct? And that is, I am just going to write the generic equation of motion. Again, this is all in classical mechanics, okay? That's the Euler-Lagrange equation. So I'm sure you remember this, right? What are Qi and Qi dot? Qi are the coordinates in the problem, right? When you want to write down kinetic energy and the potential energy, Qi are the basic coordinates that you use. Qi dot are in a sense the velocity or the momenta, the conjugate momenta that you put into the problem, correct? Okay. So when we want to derive equations of motion in field theory such as the Klein-Gordon equation, right? We had this, correct, as the Klein-Gordon equation. I'm just going to start writing phi, okay. Phi is a good symbol to denote fields that don't carry spin, spin zero fields, okay. And earlier I used to write x comma t, but now I'm just going to write x. Why? Because earlier by x I meant actually the 3 vector x, but now by x I'm going to mean the 4 vector x. So I'm just going to start using x here from here on, okay, because we are already in relativistic theories, correct. So if I want to get equations of motion for fields such as this, then I need to slightly rethink how I write the action, and in particular how I write the Lagrangian involving these fields, okay. So in other words, the Lagrangian will be actually a function of fields, but not only fields. Back here the Lagrangian was a function of derivatives of the coordinates, right. So similarly I can write my Lagrangian as a function of derivatives, however these are 4 derivatives, right. We are in relativistic theory again, so we should think in terms of 4 derivatives. We should put space and time on the same footing, right. So derivatives of fields in some combination and so on, okay. And if you already know the equation of motion, it takes some experience and practice to find out exactly what the Lagrangian is, such that using the Euler-Lagrange equations for field theory, you get back your equation of motion, okay. So can you guess how the Euler-Lagrangian equations would look like in field theory now, just from looking at this? What is the field theory analog? It should look like this, agreed? Just like d by dt, now I have to put space and time on the same footing, so I'm going to take the 4 derivative, and then I should I'm going to write the Lagrangian with a curly L now. We'll see why in a second, okay. So I'm going to take the derivative. Here I had a q dot, but instead of q dot I'm going to have the derivative again of the field, not the derivative, the 4 derivative, I'm sorry, okay. And then I'm going to label it with an I. The I are basically the components of the field, just like you had qi to stand for x, y, z, right. Similarly the field can also have components. These are not particularly spatial components, okay. You could have multiple components of the same field, right. So multiple orthogonal components of the same field. So on the left hand side I would have this, and on the right hand side I have, again instead of the coordinate I just have the field sitting over there, agreed. This is the field theory analog of the equation of motion. So let me just write, or the Euler-Lagrange equation of the theory, okay. So why did I write a curly L there, not a capital L? That's because we already saw this in the case of the Klein-Gordon equation. The Klein-Gordon equation is manifestly local, do you agree? It all happens in one point in space-time, right? So the derivative is in one point in space-time, the field I'm writing as one point in space-time, of course m square doesn't matter, right? So since it is local, and I can assure you that any equation of motion that you write down in quantum field theory will be local, we are describing local phenomena, I can write in the action, okay. So what was the action? It was this, right? I can write the Lagrangian as an integral of the volume element times this curly L. Okay, so this should tell you what this curly L is. That is not really the Lagrangian, it is the Lagrangian density. Important important thing to distinguish. Okay, so that's why in field theory we could have written an equation of motion for the Lagrangian, but it's much simpler to write it for the Lagrangian density itself. So once I have it this way, it's convenient to write the measure as a d4x, and then of course the integrand is still the Lagrangian density. Alright. Now here is the key thing here. You know what is this measure, is this Lorentz invariant? Of course it is, right? I just said it's all a local theory. So you know the way by construction here, if I were to go to another inertial frame where I measure where I have coordinates denoted by x bar, that has not transformed. So that's a Lorentz invariant, correct? And then we just made such a long, I mean we had such a song and dance about the equation of motion, the Klein-Gordon equation in this case, having to be Lorentz invariant, right? Both the field was a Lorentz invariant in that case, and the equation of motion itself was Lorentz invariant. In other words, since all of this stems from the action is also Lorentz invariant. It has to be, right? We want a explicitly Lorentz invariant theory. So that would mean that when you write down a Lagrangian to describe your theory, you better make sure that it is also Lorentz invariant. So sometimes I use the word Lagrangian to denote Lagrangian density, okay? That's the general usage. So sometimes I might slip into saying that, but remember from here on when I say Lagrangian, I actually mean the Lagrangian density. Okay? So this you should never forget. Whenever you look at a Lagrangian or whenever you try to construct a Lagrangian, make sure that it is Lorentz invariant. We are dealing in flat space time. Everything is Lorentz invariant from here on. Okay? Alright. So let me just explicitly write. That's what this means. In the new frame, you get the same. To be even more explicit, that's what this means. Okay, whatever combinations of fields I put, I should satisfy this condition. Okay, excellent. Now, what is the Lagrangian from which the Klein-Gordon equation comes? Okay, now this is something I cannot very easily teach. This is something that only comes from experience. What you have to do to get a Lagrangian is to take your equation of motion and do some trial and error with various terms that you can write down, such that if you were to take the equation of motion, if you were to take the general formula for the equation of motion, the Lagrangian should give you the Klein-Gordon equation in this case. Okay, so it's not so easy to just take the equation of motion and then integrate it on both sides and then write down the Lagrangians systematically. I'm sure mathematicians can do it, but in physics we operate mostly via trial and error. Correct? If it works, we stick to it. So I'm just going to write for you what the Lagrangian is for the Klein-Gordon equation. It turns out that this candidate, where I put two derivative terms together, oh I'm sorry, that's a 2. Okay, you can go and convince yourself that if I take this as the Lagrangian density and I plug it into the general equation of motion, I will get the the Klein-Gordon equation. Okay, but there are certain reasons to be sure that this is the Lagrangian. Okay, for example, look at how I've written the Lorentz indices. This derivative is a contravariant vector and this is a covariant vector, correct? So I've made sure that explicitly this term with two derivatives put together, explicitly it's a Lorentz invariant term, correct? Explicitly this entire combination is a Lorentz scalar. Similarly, this is even more explicitly a Lorentz invariant term, right? So we know that phi is a scalar field already. So whatever any power of phi should also be a Lorentz scalar. M square is again clearly Lorentz invariant, it's an invariant mass. So this qualifies as a candidate as far as Lorentz invariant combinations go, right? Also notice that I could have normalized this entire Lagrangian, right? I could have multiplied this entire Lagrangian with some number, let's call it kappa, and it would have been fine, right? I could have gone back and plugged this in. On both sides I have the Lagrangian density, on both sides I'll just have kappa sitting outside, the kappas would just cancel and I get the Klein-Gordon equation, right? So I chose one particular normalization here, one particular kappa, in this case it's 1, right? And that has to do with what happens with the stress energy tensor and so on. Okay, if I want to get sensible values for what the energy of the system is and so on, then I have to choose my normalization carefully. This way of normalizing, writing the first term with a half, this with the mass term also with a half, this is called the canonical normalization. What is canonical? You follow a canon, that is you follow a convention that makes sense. Right? Okay, so I'm going to erase this part because I want to write something more. Okay, so I've already chosen the canonical normalization. Can I add anything more to this Lagrangian density beyond what I've written using the fields? Can I add another Lorentz invariant term that would still satisfy the equation of motion here? There is a very trivial term that I can write down, right? Namely, I can just add, I can just add a simple number. It's just a number. Agreed? It doesn't contain fields is what I mean. Right? And of course it's Lorentz invariant because it's just a number, and if I plug it into the equation of motion on both sides, I'm going to take the derivative, it goes away. So this is something else that you should remember. When you write down a Lagrangian, there is not a single term that you should miss. Okay? So I believe it's Murray Gell-Mann who said this. In nature, if something is, this is so important, I'm writing this down, okay? If something is allowed, it is compulsory. If this term is allowed, you have no option but to write it down. It satisfies the symmetries that you want in your problem, in this case Lorentz invariance. It is a candidate, I mean there's nothing wrong in putting it into a quantum field theory. It satisfies the equations of motion, so you absolutely have to write it down. It is part of your Lagrangian density. It is a physical thing. Okay, This is a principle that we'll keep using again and again. This is one of the cardinal rules of writing down a Lagrangian. Any term that is allowed according to the symmetry requirements, you should write down. Okay, because it will have physical consequences. Okay, because this is more fundamental than the equation of motion itself. Writing down these Lagrangians that you plug into the action, that is an even more fundamental thing than the Klein-Gordon equation, etc., etc. All right. Now, I kept saying that this omega naught is a number. Do you really mean a number? As in, is it a dimensionless number? To answer that, we should ask the question, is this curly L, this Lagrangian density, is this a dimensionless quantity? No, it is not. How do I know that? This is where our lesson on natural units comes in. Take the action, okay, this is the action, right, okay, oh sorry, okay, is the action a dimensionless number? Of course it is, right? So I'm going to write dimensions, and as you can see, the action itself has dimensionality of 0. That is still a number, right? In classical mechanics it was just a number. Similarly, here also that is still a number. It's a number that you are trying to minimize, right? You want it to be on a stationary point. Okay. In that case, what is the dimensionality of the measure, the integration measure d4x? It has 4 units of length, right? Length and time are the same, remember? So in natural units, where I'm going to express everything in terms of energy, right? So let me, only once I'm going to write this, explicitly everything is in units of energy. In these units, the dimensionality of the measure is, what is that? It's just -4. Remember we saw that length and energy had inverse dimensionality, right? So this is -4. So then you can answer me, what is the dimensionality of the Lagrangian? That is 4, the Lagrangian density, right? It goes as 4 powers of the energy. Okay. Now from that, you can answer what is the dimensionality of this omega naught term that I've written, this constant term that I've written, right? So since the Lagrangian density has dimensionality of 4, it means omega naught also has a dimensionality of 4, correct? So if you think about it a bit, the Lagrangian density is nothing but an energy density, right? After all, this is in classical mechanics, kinetic energy minus potential energy. In a sense, that is what this is, right? So the Lagrangian itself has units of energy. That means the Lagrangian density has units of energy density, energy over volume, right? So in a sense, this omega naught, not in a sense, literally, the omega naught contributes to some energy over volume. Okay. Now let's look at 1 or 2 more aspects of this. What is the dimensionality of the field itself? Would the field have any dimensions? Does it carry any energy and so on? It does, right? We know already that the electric field and the magnetic field carry energy, right? Remember the Poynting vector and things like that? Similarly, over here, since the Lagrangian is constructed from these fields, the fields obviously do carry units of energy. In fact, they carry energy and hence they have units of energy. Okay. So what is the dimensionality again? The simplest thing would be to look at this term. Okay, there's already two dimensions of mass or energy. That should mean the field square has dimensions of mass squared. So the field has dimensions of 1, right? You can see that from this term also. So there are two space-time derivatives, and remember length and time have inverse dimension of energy. So this is inverse length, right? So this is there's an x mu in the denominator, another x mu in the denominator. So again it tallies, correct? The field squared has dimensions of energy squared. So the field has dimensions of 1. Agreed? Now this is true for scalar fields. It doesn't hold for fermion fields. When we talk about fermions, we'll catch up on what is the dimensionality of those fields. Okay, this is true of scalar fields, and we'll see soon that it is true of vector fields also. Okay. Okay. Now there's one more thing I can do. There's one more thing I can state here. So the Klein-Gordon equation contains two terms, right? This is, what is this? This is ultimately what becomes the mass, right? This is what we haven't identified it as such, but that's literally what we mean by the mass of a field. And since particles are excitations of these fields, that is what becomes the mass of the particle also. Okay. Now what is this then? Is it fair to call it a kinetic term? Because it acts like a kinetic energy, right? Agreed? That is literally the kinetic energy. Although this is it's not just half mv squared. This is acting on both time and space coordinates. So in some sense, it is the relativistic kinetic energy. In some sense, right? Not the real kinetic energy. That means I can give these terms a name, right? In the Lagrangian, I can call this whole object the kinetic term of a Lagrangian. Every time you see a combination of derivative fields, start thinking that's a kinetic term. Why? Because that's what gives rise to the kinetic energy term in the equation of motion. So this I can simply call the mass term for obvious reasons, right? Okay, this I can just call a constant term. There's always a constant term that you can write. Okay, excellent. So with that in hand, let's inspect the Hamiltonian. So when we talk about Lagrangians, what is always the next thing we talk about? The Hamiltonian, obviously, right? And I'm not going to just start writing down the Hamiltonian. I'm going to make use of certain features of the scalar theory here, the free scalar theory, to write down the Hamiltonian in a pretty compact way. Okay. So to do that, let us start with solutions of the Klein-Gordon equation. Okay. So I did not say this at all explicitly, but it must have been clear from looking at the equation already, right? That it is after all a wave equation, right? A free propagating wave. Agreed? That's what Maxwell also noticed for source free terms, for the source free Maxwell's equations, right? That the E and the B fields could combine to form a free propagating wave. That is exactly what we are doing here also, except this is not a vector field, this is a scalar field, right, only 1 degree of freedom. So, in other words, a solution that I can write down for the Klein-Gordon equation, in fact a unique solution would be to write it as a plane wave, right, of the form. How does a plane wave look like in general? I can write this k as the propagating momentum, right, and then generically there is a plus or minus, and there is some energy associated with the wave, so that I can write it this way. Agreed? It is a combination of sine and cos, right. So, you can go convince yourself. So, this is again I am going to write down the Klein-Gordon equation for your benefit. That is what it is. Am I missing a minus sign? Yeah, of course I am. So, that is what it is. So, you can plug this into the field and convince yourself that that is indeed a solution. Okay. All right. So, I am going to wrap up this class by writing out the solution for the field in terms in even more broader terms, and then in the next class we will take up some relations between the operators that I am going to write down. Okay. So, in general this would mean I can do a mode expansion on the fields. Agreed? And for convenience I am going to separate the x, the 3 vector position from the time, right, because we have already done that when we wrote the plane wave equation, plane wave solution, correct. So, would you agree that I can now write the solution as some measure, which I will get to in a second, times some coefficient, okay, times e power I k dot x minus omega t plus another coefficient, another arbitrary coefficient times e power I k dot x minus omega t, propagating in one direction versus propagating in another direction. Sorry, over here I put minus, right. So, here it is a plus omega t. This is propagating in the other direction. Would you agree this is the most generic solution in terms of plane waves? And what is this? Why did I write it in this odd form? I want to ultimately write a Lorentz invariant measure. Okay. So, I want to find out what the Lorentz invariant measure is. So, since I do not know how to derive it yet, but we will see it soon, I am just going to write a generic function f of k in the denominator, just to remind myself that this combination is Lorentz invariant. Okay. Now, what is the relation between omega and k here, because it is a plane wave? It has to be this, right. Omega is k square plus m square, that is this particle is on shell, right. So, this is the relation that I put in to get a plane wave solution. Okay. So, I will stop here. Now, we will take up this solution and look at some of its properties and derive the Hamiltonian, and from there we will see where the cosmological constant problem arises from this. Okay. All right. See you in the next class. Thank you.